Hello guys, welcome to FreeBirds2 and welcome to 75-day Hard Generative AI Learning channel. This is day 64. And in the last videos, you see how quantization works in detail with mathematics. So in this video, I will tell you about 1-bit and 1.5-bit large language model quantization techniques that are the best in the industry right now, because they can increase the efficiency by 300 times and can decrease the model size by 400 times. So let's get started. Okay, so very first thing, let me give you a summary about the quantization levels that are already achieved just before the 1-bit quantization techniques. So when we are doing the large language model training, the parameters that are learned in the 32-bit precision format, however, for the storage and the deployment, they are quantized to the 16-bit precision, so that we just reduce the size but not by very much. Okay, so this lead to very minimal accuracy loss with considerable reduction in the storage requirement, because we reduce the size from the 32-bit floating precision to the 16-bit floating precision. Okay, so the next quantization level is when we quantize the 32-bit precision format to the INT8-bit precision format. So it reduces the memory footprint by a very large chunk, but also a great loss of accuracy as well. Okay, and the next thing is called as INT4 quantization. So in that, we convert the 32-bit precision to the 4-bit integers or specialized data types like normal float. Okay, so these are the quantization levels that are already achieved. Okay, now let's talk about when to apply the quantization. The very first technique is called post-training quantization. So this will happen when you already have a pre-trained large language model which has the 32-bit precision formats weights. So you quantize those weights to the lower format. Okay, the next technique is called quantization aware training, that I already explained in my previous videos as well. So in this quantization, you add a new kind of a layer of weights and activation function to the model, so that when we are fine tuning or training the model, those quantization aware training injects operations like scaling, clipping, rounding of parameters as well. So this complete things lead to the quantization error in model calculations. So this quantization error is then added to the loss function, and then the optimizer tries to update the model weights to minimize this new loss, because this new loss is not only the large language model loss, it also the loss of your additional quantization error as well. Okay, so in that way, your model will become more robust to the eventual quantization after training. Okay, and you can use these kind of techniques like LoRa, QLoRa, and general pre-trained transformer quantization, and along with the adaptive weight quantization techniques as well. I will explain about these techniques with the Python code in my next video. Okay guys, okay, so now the new technique comes, that is called 1-bit large language model and 1.5-bit large language model. Okay, so the 1-bit transformer architecture of large language model, it contains a linear layer of the original transformer architecture with the new bit linear layer, which enables the revised architecture to train the 1-bit weights. Okay, so experimental results on the large language model shows that this bitnet achieves competitive performance while substantially reducing the memory footprint and energy consumption as compared to our INT8 quantization method as well. Okay, and just like the original transformer architecture, this bitnet layer also has the self-attention feed-forward neural network as well. And the matrix multiplication operations in the bitnet use the binarized model weights. Okay, it don't use the complex matrix multiplications. Okay, and first, the weights we have in this bitnet layer are centralized to the zero mean, that they become binarized to the +1 or -1 as well, so that the positive weights will get the +1 and the negative weights will get the -1. Okay, and then we have the scaling factor. The scaling factor is used to reduce the error between the real value and the binary weights, and the activations are quantized to the b-bit precision that can be 8-bit or 4-bit as well. And this architecture use the model parallelism, so that matrix multiplications are all happen on the distributed computing method. Okay, and the model is trained by using the straight through estimator to compute the gradients while doing the back propagation. So in that way, this whole training will happen. So if you have the transformer architecture in the 16 or 32-bit precision, so you can easily convert it into the binary format with the help of this new bitnet layer. Okay. So now let's talk about 1.5-bit, because we have this 1 bit that can have the 2 digits, +1 and -1. But in 1.5-bit, we have the 0 as well. So you can just imagine it like a case where you have the +1, you have the -1, you have the 0. The Z0 means a neutral weight or no weight as well. Okay, so this architecture gives us a strong memory and computational cost saving as compared to the conventional transformer based large language models. Okay, so now the question comes that why 1 bit or 1.5-bit quantization does not lose the information as compared to the INT1 and INT4 quantization, because I already explained in my last videos that INT1 and INT4 quantization lose information very much, and they decrease your accuracy drastically as well. So why the 1 bit and 1.5-bit are the best quantization methods? Because binary quantization represent the extreme case of quantization where numerical values are compressed into the binary representations like +1, -1 or 0 as well. So information loss is minimized because these values actually capture the direction of the values, not the magnitude of the values. So when we have the direction of the values as well, so our model can easily understand that this value is negative, this value is positive. Okay, but in the INT4 and INT1 quantization, the directions are not captured, because the range of the INT1 is from 0 to 1, and for the INT4 is from 0 to 15. So that's why you don't capture the negative values in these representations. Okay, so that's why we don't use INT1 and INT4, but 1 bit and 1.5-bit are the best quantizations we ever see. Okay, and this bitnet 1.58 matches with the 16-bit floating point large language model in perplexity end-to-end task performance as well, and it provides faster computation speed and use the less GPU memory as well. This model minimizes the multiplication operations for metric multiplications, enhances the efficiency, and include a quantization function for system level optimization, and integrates components like RMS, norm, and FIGLU that is similar to the LLAMA. Okay, so if you want to know more about the fine-tuning techniques like LoRa, QLoRa, along with you can apply it on the many kind of large language models like Databricks language model, Google Gemini or Gamma, then Meta and Microsoft Feed 2. You can watch all the videos. I will put this notebook link into the video description. You can check it as well. If you need the one-to-one mentorship in the data science, AI and generative AI, you can book a call with me on this link as well. Alright guys, so just be with it, and if you want to know more about generative AI, prompt engineering and data science, you can watch my videos on YouTube and also read my blogs on Medium. We'll meet in our next video. Thank you so much.